let's see, how do we tune the electrical conduction properties of semiconductors? Again, we have to dope them. We add impurities to them. It's called doped instead of intrinsic semiconductors. There are two types of doping schemes when it comes to producing impurity semiconductors. Impurity or doped semiconductors. The first is called N-type. So what we do here is that we start with a pure piece of silicon or germanium, group 4, and we dope it with group 5 atoms. Basically, we replace a small fraction, let's say 1 in a million, 1 in 10 million of these group 4 atoms with a group 5 atom, okay, such as phosphate, group 5. Now, group 5 atoms has one extra valence electron, right? One extra valence electron, and it replaces, this group 5 atom replaces a normal group 4 electron atom here. So it's got an extra valence electron, which is kind of useless because the surrounding atoms are all group 4 atoms. So we got 1, 2, 3, 4, 4 valence electrons, one contributing to each bond. This guy, the fifth one, is like an orphan. You don't quite need it, right? This guy, so this group 5 atom does not quite care about this one extra electron because it's not that useful. Now, it doesn't mean that it doesn't want it, because there's always still a Coulomb attraction between positive and negative. So it's not like it's entirely free. You can just, it will just get out of here by itself. But we can say that it is only very loosely bound to this atom. It doesn't take much effort to pull that electron out, because again, that electron is not that useful. Okay? So therefore, a little bit of effort and this electron will just be pulled away from its host, and therefore it becomes a free electron. Free electron means it has now entered conduction. It will be at the bottom of the conduction band. Here is the bottom of the conduction band. Where does this electronic level sit? Just a tiny bit below the bottom of the conduction band, so that you give it this much energy, which is all the energy it needs to pull the electron loose, so that it enters the conduction band, it's free to go. Okay, so this is why we dope it with group 5 atoms, because you have now created a level, a discrete level of electrons a little bit below the bottom of the conduction band. Normally, in the gap, there is nothing, right? Here you have one discrete level, and you have these electrons. This is where these, the blue electron sits at this level. Okay, for each impurity atom, group 5, you have one such atom, such electron. Now that electron doesn't take too much effort to be pulled out from here to there. Once it enters the conduction band, it will be contributing to electrical conduction. What is the energy it takes to go from here to there? It's a lot less than Eg. Okay, Eg is about 1 eV, but this is only 0.05 eV, which is comparable with kT. Right? kT is 1/40 of an eV, and therefore you have just created a case where you can get conduction electrons from this added new energy level. This new energy level donates electrons to the conduction band, so we call it the donor level. Donor level, and these atoms are called donor atoms because they each can contribute an additional electron, which will be available for conduction. And when we dope this semiconductor with different percentage of group 5, we can then control the density of these donor electrons. Therefore, we can dramatically change the conductivity of this semiconductor material depending on what's the concentration of doping. That's how N-type semiconductor work. Why do we call it N-type? It's because it is the electrons, not the holes, that are producing conductivity. Okay, the valence band is essentially still empty because that gap is too large, and therefore it is basically the electrons, or negatively charged particles, N standing for negatively charged particles, that are contributing to electrical conductivity, so we call it N-type. Now here comes the second type of doping scheme, and that is we're going to replace a group 4 atom with a group 3 atom. Okay, so this time it's a group 3 atom, such as aluminum. And the thing about that is that this aluminum, it doesn't have enough valence electrons, right? It is missing one valence electron. So this red circle denotes a missing electron. A missing electron. And the missing electron behaves like a hole, you know, just as we saw before, right? So this guy, just like the previous case, will create another discrete energy level inside the otherwise forbidden gap between the top of the valence band and the bottom of the conduction band. The question is, where does this discrete energy level sit? Where in the energy band does it sit? Well, the thing about it is that ideally you would want that electron here, right? You would want that electron here. It's missing, and therefore it's highly desirable to have an electron there. And therefore, it doesn't take much effort to promote an electron from somewhere inside these atoms to here, because this is a desirable spot. If you had an electron there, it's going to fill all the bonding, right? That's the number of valence electrons you need for the bonding. And again, where does the electron come from? It comes from within this atom. It comes from the valence band. Okay, and of course the easiest thing to do is to promote an electron from near the top of the valence band to here. It doesn't take much effort, and therefore this electronic level would be somewhere just above the top of the valence band instead of near the bottom of the conduction band. Okay, so an electron from near the top of the valence band, you give it a little bit of energy, it's going to go there, and that is another discrete energy level which sits in the forbidden gap, and we call it acceptor level. Why do we call it acceptor level? Because normally this level is empty, but it can accept electrons from the valence band, so we call it acceptor level. Okay, once an electron is promoted from the top of the valence band to this acceptor level, this electron is out of commission. It's in a discrete energy level. It cannot contribute anything to electrical conduction. However, it left behind it a hole. And this hole can conduct electricity because the valence band is now partially empty because of this hole. Okay, the valence band starts to conduct electricity. So this time, it is the positively charged holes that are contributing to electrical conductivity, so we call it the p-type semiconductor. Again, it doesn't take much effort to promote an electron from here to there. It only takes about 0.05 eV, which is very easy to do, and therefore, by doping an otherwise pure piece of silicon or germanium with group 3 atoms, we can create these acceptor levels, thereby creating these holes, which will turn this into a much better conductor. And the conductivity, again, depends on the level or concentration of doping. So now we have two types of impurity semiconductors, N-type and P-type. They can both contribute, they can both conduct electricity with variable amount of electrical conductivity, depends on the level of doping. But why do we need two different types of doped or impurity semiconductors? Is there any advantage to having two different types of impurity semiconductors? And the answer is a resounding yes, because it turns out that we can put these two types of impurity semiconductors together, the P-type and N-type, and create magical devices out of them. So here we see what's called a p-n junction. This is when we put a P-type semiconductor and an N-type semiconductor, both are doped, so doped type impurities. We put them together in contact so that electrons and holes can hop back and forth. Okay, this is called a p-n junction. The p-n junction is one of the most important, interesting devices in microelectronics because of its interesting properties. Let's see. If I start from this is the P side, and here's the N side. Okay, P side and N side. To begin with, the P side and N side, P standing for positive, does that mean this piece of semiconductor is positively charged? Does that mean this piece of semiconductor is negatively charged? No way. Okay. Why do we call it N-type? It's because we have, some of the atoms belong to group 5, right? So they have an extra electron in the valence band compared with the group 4. But don't forget, these are group 5 elements. They also have an extra proton, don't they? Okay, so that balances out, okay? The total number of the net charge in P-type and N-type were 0 to begin with. They both 0. Now you put them together so that electrons can hop back and forth. Holes can hop back and forth. Now, what's the situation? Well, on this side, you have a bunch of holes because they are, after all, this is the P-type, okay, the P side. And, and on that side, you have a bunch of ends, which means electrons. Okay, so you got some positive charge holes that fill this region, negative charge electrons that fill that region. Normally, they are restricted to within a body of each other, but now that we weld them together, we put them together, the holes will start to migrate. Some of the holes will start to migrate across this border, and some of the electrons will start to migrate. This is called drifting, okay? Drifting. It's the same as, you open a bottle of perfume, and eventually the perfume atoms, the perfume molecules will be filling the entire room. The same idea, okay? Now that you allow the holes to go this way, they will. You allow the negative charge electrons to go that way, they will. So the holes will start to migrate this way. Migrate this way. Now remember, the p side was initially charged neutral, right? Some of the holes will now go this way. So they're going to lose some of these positive charge holes. So you get some positive charge holes on this side. And then this whole thing becomes negatively charged as a result. But don't forget, the electrons on that side also will start to drift. They also start to migrate. So some of the electrons will cross the gap to go that way. And as they do so, they will produce some negative charge on this side. This will further enhance the negativity of this side. So this side is now negatively charged. Okay? Same thing can be said on that side. First of all, it loses some of the electrons through migration, and secondly, it gains some positive charges from that side through the whole migration. So these two effects enhance each other. So eventually, you're going to have some positive charge on this side. So believe it or not, when you put an p-n junction together, you'll find the p side eventually become negative charged, and n side actually become positive charged. Isn't that interesting? Okay, so before you did that, the potential was 0 here, the potential was 0 there. Now, because of the migration of electrons and holes, you can have excessive positive charge here and excessive negative charge here. So now there is a potential barrier like this. That's this diagram. Okay, the n side being positively charged has a higher potential than the p side. Okay, the drifting of positive charge holes this way will have to overcome this potential barrier. Initially, the potential barrier is pretty small because you don't have a lot of positive charge migrating over. So you don't have to scale a very tall mountain to go from here to there, the holes, and therefore the holes can easily migrate over. But gradually, they're going to build up a higher and higher barrier, so the holes will find it more and more difficult to go from here to there. Eventually, the drifting will stop when this barrier is tall enough. Okay, when this barrier is tall enough. Similarly, the electrons going from here to there will also encounter a barrier because this side is negatively charged. And with more and more negative charge built up, it's going to create a taller and taller barrier. So eventually, the migration of electrons from here to there will also stop. Now, so this side will build some positive charge, this side will build some negative charge. There is a transition region in between the p side and n side. This is called depletion region or depletion zone in most textbooks, depletion zone. Why do we call it depletion zone? Because this is where you have a lot of cross traffic, electrons go this way, holes go that way. And as the electrons and the holes meet each other, what happens? They will recombine because positive and negative charge attract each other, right? They will recombine, so you don't have that hole anymore, you don't have the electron anymore. This is a region where you don't have a lot of holes and don't have a lot of electrons. It's called depletion zone. Okay, so you see, when you put an p and n together, initially there are a lot of migration, cross traffic going on, and eventually when the barrier is built up, the migration will stop, drifting will stop, and because of this barrier. This is what happens in a natural p-n junction. How do we take this device and put it to use? Well, we want to connect it to a potential difference. And depending on the polarity of that potential difference, we will get totally opposite results. There are two ways to connect this p-n junction called forward and reverse bias. Let's see. Forward bias for a p-n junction like this, okay? A forward bias means that I'm going to hook up this p-n junction to a power source so that this side has higher potential from power source and that side has a lower potential from power source. This is called forward bias. And the result is that you can encourage a current flowing through. Why is that true? Because remember, naturally, in a p-n junction, if you leave it alone, it's going to have a potential barrier like this, right? The n side is actually, you have accumulated some holes, so that it's actually higher in potential, V naught, right, than the p side. But when you hook up to a negative and a positive potential, that counteracts with this, right? Because the n side initially has a higher potential, but now you put in a lower potential terminal. So that extra power supply actually lowers the potential barrier, doesn't it? It lowers potential barrier. And because it lowers potential barrier, if the barrier is lower than the equilibrium value for the drifting to stop, then drifting will resume until it goes up to that again. So drifting will resume, okay? And that's the drifting current. So a lot of the holes will migrate this way, a lot of the electrons will migrate that way, each contributing to a current flowing from P to N. So this is called forward bias. Okay, forward bias. And what about if you connect it the other way around, positive and negative? You know, the p-n junction already has a higher potential on the n side, and you put it even higher by hooking up to a positive terminal. You put this even lower by hooking to a negative terminal. That is only going to make the potential barrier even taller. That's going to discourage the drifting. Okay, so very little holes will go this way, very little electrons will go that way, and as a result, you have very little current. That is called reverse bias. So you see, unlike a conventional resistor, where it doesn't matter whether you allow the current to flow this way or that way, for a p-n junction, if you connect a forward bias, allowing electrons, allowing the current to flow this way, you get a good current. If you try to hook it backwards, you try to put a current this way, you could get very little response, and that is called revert bias. So the so-called VA characteristics, that is how the current in amp responds to the potential difference in volt, is not a straight line such as in the case of Ohm's law. Rather, it's a curve like this. Okay, you see it's 0, 0, right? No. Okay, if you don't put any voltage across it and it reaches natural equilibrium, no current, drifting stops. It's like this, right? If you give it a forward bias, the current is not going up like this. Rather, it goes up like some sort of exponential curve. Can you understand that? Yes, because look, for a particle, a hole, to go from here to there has to overcome a potential barrier, right? And the potential barrier is lowered by a certain amount. So therefore, the energy it has to scale over is decreased by a factor of e to the EV naught over KT. That is the isn't that the I'm sorry, EV over KT. V is the potential difference V that you apply here. Okay, EV over KT. EV is the decrease in energy that you have to come over, the energy hump that you have to come over KT. Okay, so this is the factor by which the probability of going for hole to go from here to there would increase. That, of course, is proportional to the current that you're going to get. So, therefore, you can see here, the current goes up as an exponential function of voltage. Okay, so that's why it looks like this. And here, when it goes backwards, you increase the potential barrier, so that makes it more difficult. So it's essentially 0, basically. Now, you also have to, there's something here that's not in the textbook, but I want to tell you. There's something called the Zener effect. We can use that to build what's called an avalanche diode. The Zener effect happens when you extend this curve. Okay, when you extend this curve, when you put this on reverse bias, but with a very, very large voltage difference, then at some point, boom, you see something like this. There's a dramatic increase in current. So the reverse bias actually produces a very large current. Of course, flows backwards. And why is that? Well, that is when the electrons or the holes are exposed to such a huge potential difference that despite this hump here, they have enough potential between here and there that they just pull directly over no matter what. I mean, they're too eager to go from here to there because of the potential difference. So despite this hump here, they just fly over the hump. So it's something like this. Okay, this is called a Zener effect, which is not discussed in your textbook, but that doesn't happen until you give it a very large reverse bias. So you wonder what a p-n junction can be used for. Well, it's one of the most useful elements in all of modern electronics. And I'm here only to discuss two of the famous applications, the LED and the photovoltaic cells. LED, we use that today for display technology. We use that today for energy efficient lighting, right? An LED light uses very little electricity, and it's what's called a cold source because you can touch the LED light when it's fully bright and you don't burn your fingers because the heat produced is very minuscule. It's called cold source. This is why it's so efficient, because for regular power source, regular light, most of the energy is actually turned into heat. It's wasted, and it makes the light bulb very hot. But LED is cold source, very efficient. How does LED work? We also use it for display technology, right? LED panel. It's actually a variation of LCD, where the light source is no longer fluorescent, but the light source is LED arrays. So it's a bunch of small LED bulbs that light up the screen. LED stands for light emitting diode. A diode basically is a device made of a PN junction, light emitting diode. You know, in a PN junction, we have here's a piece of semiconductor, right? So we have a gap, all right? We have a gap between the conduction band and the valence band. And of course, if you have a p-type, n-type, there's something in the middle, but we're not concerned about those things in this context. We're just concerned about this gap in general. This gap is around 1 eV. Okay, 1 eV. Now, two things can happen. An electron in the conduction band can drop down and recombine with that hole. So it takes out that voided space, and as a result, it loses energy. This energy is given off in terms of light. Okay? This is called light emitting diode. The reverse process is that an electron can start from here and receives energy from a photon and hop onto the conduction band. This is called a photovoltaic effect, because we can use it to produce electricity out of light. Okay. In the case of silicon has a gap around 1.1 eV, which is infrared. So any light whose frequency is IR, infrared or above, will have energy above 1.1 eV per photon, and those photons will be able to take that electron across the gap. You can go from here or even to here or to here, depending on how energetic it is. And with that, these electrons will gain energy from that photon by absorbing that photon, and that energy can be turned into electricity. So that's how a photovoltaic cell works. So basically just a diode. Okay, now we know how important LED technology is, and it's only in its the application is only beginning to pick up, and photovoltaic cells are also extremely important. We can calculate the theoretical efficiency of a PN junction used as a photovoltaic cell, photocell. It turns out for an ideal PN junction made of silicon, the efficiency of converting energy of light to electricity is about 33.7%. That's called Shockley-Queisser limit. You can check that out if you're interested. It's not something very easy to calculate though, but I can tell you there is a limit, about 33%. So roughly speaking, about 1/3 of the energy of the light, of the sunlight, can be converted into electrical energy. That's a lot. Now, with current technology, the solar cells that we can buy to power our house has an efficiency somewhere between 10 to 15%, usually. Okay, if you don't go too expensive, somewhere between 10 to 15%, which is below that limit. In the lab, we can actually reach that limit. We can even exceed that limit in certain extreme circumstances. But this is roughly what we're talking about. So let's say you take a 10% efficient panel, a solar panel, which is made of a whole bunch of these photovoltaic PN junctions. And let's say the area of interception is 1 meter by 1 meter, so 1 meter squared. What kind of electrical power can it get if you expose it to regular sunlight, which has an intensity of about 1,000 watts per meter squared? About 1,000 watts per meter squared. Okay, it's 10% of that, right? So you will get about 100 watts per meter squared. If the area of the panel is 1 meter squared, you're going to get about 100 watts. Okay, 100 watts. That's a lot. That's 100 watts. Of course, this is only possible when you expose it to sunlight. What if it's not sunlight? What if it's it's night? What if it's a rainy day with no sun and so on? So you have to average over the period of 24 hours. You have to also average over the season. Therefore, you cannot say, okay, for every 1 square meter of solar panel, it's like a 100 watt light bulb. It's nothing like that. It's less than that. But let's say we give it a factor of 10. Okay. So we need 10 square meters to produce 100 watts of continuous power supply. Even that is quite a lot, because we need only a 10 by 10 meter of solar panels. That's 100 meters squared. That will give us 1,000 watts or 1 kilowatt, which is enough for most households, unless you use AC, which will take some more. So if you have a roof or hills or a slope from the hillside, which is otherwise useless, and you line it up with the solar cells, you will have enough energy. You will produce enough energy to run your household. And probably here in Southern California, because we have so much sun exposure, we will not only have enough energy to run our household, we can also sell the excess energy produced by these photocells to the power company. That is entirely possible. And it's completely clean. The energy is completely clean. The only thing is the cost. At the current stage, the cost is still pretty high for most households. So the break-even point, that is, use the same amount of the cost the same for solar power versus regular power you buy from power company. The break-even point is still pretty high. If you're not paying more than $150 or so a month in power bill, then installing such a solar panel energy system is probably not all that worth it in terms of financial cost. But as the price goes down for the solar panels, and as the price goes up for fossil fuel generated powers, the break-even point will get lower and lower, and hopefully in the not so distant future we'll see a lot more solar panels going up that will give us clean energy. And here is the physics behind it. So now we have two types of semiconductors, P and N type, and we already put P and N together. But what about if we put P and P together, or NPN? This would be called a transistor. The transistor was invented by 3 American physicists at AT&T Bell Lab, Badin, Bratton, and Shockley, in 1947. The transistor revolutionized the entire electronics industry and the entire computer industry. And it is the holy grail of modern electronics. Extremely important. The primary purpose of a transistor is to produce amplification of electronic signals. So how does it do that? How does a transistor work? Well, I have here some diagrams from the textbook. It tells you how a transistor works. But here is a symbol that we usually use in most textbooks for transistors. Okay, here is the symbol for transistor. A transistor has 3 terminals. There is E, there's B, there's C. E standing for emitter, B standing for base, and C standing for collector. In this case, this is the emitter, this is the base, and this is the collector. So here's how it goes. How does this PNP or NPN junction produce an effect of amplification? All right. Using NPN as an example, right? You got electrons coming out from here. The electrons are emitted from this side. So it's called emitter. This is called emitter. Electrons emitted this way, so the current flows backwards, right? The current flows this way. Electrons flows this way. And part of the electrons, if you add a little current loop here, part of the electrons will get drawn this way, and it's forward biased. You see here, the electrons between B and E, it's forward biased. So the electrons, part of the electrons will go this way. But the thing is that on this base, I make it very thin. I make this base very thin, so there's very little, relatively speaking, very little current goes this way. Remember, these are negatively charged particles. These are electrons. Electrons going this way. And on this loop, I have a I have a power supply like that. That's actually reverse biased, but it's positive side here. So the electrons, small amount of electrons will go this way. Most electrons will be happy to go that way because they will meet a positive terminal here. Okay, they are attracted this way. So the current from the emitter produced by a beam electrons going this way, small fraction of that current will form this loop. The majority of the current will go that way. So you will have a larger, considerably larger amount of current flowing through the collector, a smaller amount of current flowing through the base. In other words, IC is a fraction, is a large multiple of IB, beta. Beta is called the gain factor, which can be typically a few hundred for a transistor. So if you have an input signal, you have an output signal, the output signal can be several hundred times as the input signal. So this is how the transistor can act as a amplifier. And one of the best things about semiconductor devices is that I can make these transistor and diodes extremely small, microscopically small. Then I can squeeze so many of them onto a very small space, which is called an integrated circuit, IC. And this is how modern electronics are built, on a chip, on a silicon chip, okay, with millions and millions of transistors and diodes, all these things, squeezed on a square inch. And the denser these elements are per square inch, the higher the performance of the chip. And when it comes to performance of the chip, there is a famous law. I'm sure you have all heard about that. It's called Moore's law. The Moore's law was first proposed by Gordon Moore, the founder of Intel, in a paper in 1965. What does it say? It says the performance of a chip essentially doubles every 2 years. We put it in mathematical form, and here's what it is. The performance of the chip, that's proportional to the density of the transistors that you can squeeze onto every square inch of the chip. And that density can increase as a function of time like this. T0 is 2 years, which was later changed by another Intel executive to 18 months, which reflects the reality better. Every 18 months, so T0 is about 18 months, so you add another 18 months, the performance doubles to 2 to the power T over T0. That is an empirical law proposed by Gordon Moore. And despite its crude nature, it is extremely accurate in terms of reflecting the reality. Here I have a plot from the textbook. The millions of transistors you can put in on a chip, and that number increases non-linearly because it's a power function, right? It's non-linearly, so it initially starts slow and gradually gets faster and faster. Now picks up like crazy, like this. Okay, but since this is a power law, it's better to plot it naturally as a power. So here is linear year. This is unlike here, this is the linear scale, right? Linear scale. Here you have a power scale, okay, 10 to the 3, 10 to the 4, 10 to the 5, and so on. And on this power scale, you see you got almost a straight line. These are all real chips, okay? These are all real chips. I486, that's a famous CPU. It's about, in the late 1980s. And then Pentium, Pentium Pro, Pentium 2. And all these things, look at this, almost falling to the same straight line as predicted by Gordon Moore. Where are we? We're somewhere here. We're somewhere here. Okay, will this straight line continue? Well, I think it's going to continue in the near future, for some time to come, but only in the near future. If you ask most people in the know, they will tell you, they probably tell you that this trend is not that far from its last leg, because we have to squeeze more and more performance out of the IC chip made of tiny silicon components. As we squeeze more and more of these elements, tiny elements, onto denser and denser IC chip, we will inevitably reach the quantum limit, and that is the wave nature of particles will start to interfere the performance. You cannot just make something incredibly small. You're gonna encounter Heisenberg's the principle type of thing. So looks like in the foreseeable future, the Moore's law will stop working for silicon, which means you cannot expect to continue to pay less for a better computer at today's pace. At some point, this trend is going to stop. What does that mean? It means it is time for us to look into something new, something that replaces silicon as the next revolutionary technology for microelectronics. This should happen within our lifetime, and probably sooner than that.